Good evening all. Myself P. Chakradhar from ECE Department A section. Today our topic is modulation compression in next generation RAN. Generation RAN, air interface and morphofunctional trade-offs. Introduction of modulation compression. Modulation compression is a technique designed to enhance the efficiency of data transmission in wireless network. It plays a curricular role in optimizing the air interface and most connections in next generation RAN. RAN full form is Radio Access Networks. Understanding these trade-offs is essential for improving network performance and resource utilization. Data we can see in this picture data compression technique model. Data compression models. There are two types models, lossless models and lossy models. Next one, importance of next generation RAN. Next generation RAN aims to support advanced applications like LOT, augmented reality, and ultra reliable low latency communications. The demand for higher rate higher data rates and lower latency is driving innovations in modulation schemes. Modulation compression can significantly contribute to meeting these demands by optimizing spectral efficiency. Overview of modulation techniques. Modulation techniques are methods used to encode data into carrier signals for transmission. Common techniques include QM. QM full form is quantitative amplitude modulation. PSK phase shifted killing and OFDM or orthogonal frequency division multiplexing. Each technique has its advantages and trade-offs in terms of complexity, bandwidth efficiency, and resistance to noise. We have a graph. In this graph, blue and yellow lines are. Blue line is phase signal component and yellow is quadruped signal component. Next one, modulation compression. Definition of mechanism. Modulation compression reduces the required bandwidth for a given data rate without sacrificing quality. It is achieved by efficiency packing data into modulation symbols, reducing reducedly and improving transmission efficiency. The technique is particularly beneficial in scenarios with limited bandwidth, limited bandwidth or high user density. We have a picture stream generated by vapor compression and recycled bin and vacuum gas release. Challenges is in air interface design. The air interface is curricular for wireless communication, affecting, affecting how signals are transmitted and received. Key challenges include managing interfaces, ensuring robustness against fading, and optimizing resource allocation. Modulation compression introduce additional complexity that must be managed to maintain reliable communication. Trade-offs in air interface performance. Implementing modulation compression can lead to improved spectral efficiency but may increase decoding complexity. The choice of modulation scheme impacts the trade-off between data rate and error performance. System System designers must balance this factor to optimize overall network performance. Next one, fractional HU structure in 5G networks. Fractional refers to the connection between the criticized cloud and distributed radio units in RAN. It is virtual for transporting high bandwidth signals with low latency to support advanced services. The architecture must accommodate various traffic patterns and service requirements efficiently. Trade-offs in frontal design. Frontal design involves trade-offs between capacity, latency, and cost. High-capacity frontal connections can handle increased data rates, but many require significant investment. Latency-sensitive applications may necessitate suspensive functional solution to ensure timely data delivery. Impact of modulation compression on functional. Modulation compression can reduce the amount of data transmitted over the functional, evaluating bandwidth constraints. It can also lower latency by decreasing the time required for data transmission. However, careful consideration must be given to ensure that the benefits do not compression signal integrity. Next one, case study. Modulation compression in action. A real-world case study demonstrates how modulation compress improved work performance in a dense urban environment. The implementation resulted in a significant increases in user throughput while maintaining low latency. Lesson learned from this case study can guide future developments and automatizations. Future trends in modulation techniques. Future research is expected to explore advanced modulation techniques such as adaptive modulation and coding. Machine learning may play a role in dynamically optimizing modulation schemes based on real-time conditions. Ongoing advancements will continue to enhance the efficiency of both air interface and functional communications. We can see in this picture types of modulation. There are two types of modulation, algorithm modulation and digital modulation. In alveolar modulation, there are three phases: amplitude modulation, frequency modulation, and phase modulation. In digital modulation, amplitude shift keying, frequency shift keying, and phase shift keying. These are types of modulation. Regulatory contributions. Regulatory framework will influence the adoption of modulation compression techniques in next generation RAN. Compliance with spectral allocation and interface management is essential for successful development. Policymakers must balance innovations with the need for fair access and efficient use of resources. Conclusion Conclusion Balancing trade-offs. The trade-offs between hair interface design and functional architecture are critical for optimizing next generation RAN. Modulation compression presents an opportunity to enhance network efficiency, providing challenges and addressed. Future development will need to continually access and balance these trade-offs to meet evolving demands. Key takeaways. Modulation compression is a visual technique used for improving the efficiency of next generation RAM. Understanding the trade-offs between hair interface performance and functional design is essential for network optimizing. Continued innovation and research will derive advancements in this area, shaping the future of wireless communication. Thank you.